Hello, everyone. Welcome to, I'm going to talk about, actually, you know what, let's start this again. Okay, sorry, I need to think about how I start these. Uh, okay, let's go ahead and go live. Hello, everyone. Well, I'm here to talk about nestedly recursive functions based on a piece that I posted a couple of weeks ago now. So let's get to nestedly recursive functions. Yet another Ruliological surprise. Integers, addition, subtraction, maybe multiplication. Surely that's not enough to be able to generate any serious complexity. In the early 1980s, I'd made the very surprising discovery that very simple programs based on cellular automata could generate great complexity. But how widespread was this phenomenon? At the beginning of the 1990s, I had set about exploring this. Over and over, I would consider some type of system and be sure it was too simple to do anything interesting. And over again, I would be wrong. And so it was that on the night of August 13th, 1993, I thought I should just check what could happen with integer functions defined just using subtraction and addition. Well, I knew, of course, about defining functions by recursion, like the Fibonacci function. Show you that. But could I find something like this that would have complex behavior? I did the analog of what I've done so many times and just started symbolically enumerating possible definitions. And immediately I saw cases with nested functions like, oops, like, like this. For some reason, at the beginning, I wanted to keep the same initial conditions as for Fibonacci. That's f of 1 equals f of 2 equals 1. So what would functions like this one here do? Well, my original notebook from that time records the result in this case. But a few minutes later, I found something very different. A simple nestedly recursive function with what seemed like highly complex behavior. I remembered seeing a somewhat similarly defined function discussed before, but the behavior I'd seen reported for that function, while intricate, was nested and ultimately highly regular. And so, as far as I could tell, much like with Rule 30 and all the other systems I'd investigated, nobody had ever seen serious complexity in simple recursive functions. It was a nice example, but it was one among many. And when I published A New Kind of Science in 2002, I devoted just 4 pages and 7 notes to recursive sequences, even though the gallery that I made of their behavior became a favorite page of mine. Well, a year after the book was published, we held our first Wolfram Summer School. And as an opening event, I decided to do a live computer experiment in which I would try to make a real-time science discovery. The subject I chose was nestedly recursive functions. It took a few hours, but then, yes, we made a discovery. We found that there was a nestedly recursive function simpler than the ones I discussed in New Kind of Science that already seemed to have very complex behavior. Here it is. Well, over the couple of decades that followed, I returned many times to nestedly recursive functions, particularly in explorations that I did with high school and other students, or in suggestions I made for student projects. Then recently, I used nestedly recursive functions several times as intuition building examples in various investigations. I'd always felt my work with nestedly recursive functions was unfinished. Beginning about 5 years ago, particularly energized by our physics project, I started looking at harvesting seeds that I'd sown in a new kind of science and before. So I've been on quite a roll with a few pages or even footnotes repeatedly flowering into rich book-length stories. And finally, particularly after my work last year on expression evaluation and fundamental physics, I decided it was time to try to finish my exploration of nestedly recursive functions. So our modern Wolfram language tools, as well as ideas from our physics project, provided some new directions to explore, but I still thought I pretty much knew what we'd find. And perhaps after all these years, I should have known better, because somehow in the computational universe and in the world of Ruliology, there are always surprises. And here, yet again, there was indeed quite a surprise. All right, the basic idea. Consider the definition that we'll later call P312. And the definition, I don't know what that brace F is doing at the beginning, but the definition is just saying F of n blank, any value, such that n is less than or equal to 0 is 1, and F of any other value, n, is 3 plus F of n minus F of n minus 2. We can also write that in this form here. If n is less than or equal to 0, then 1, otherwise 3 plus F of n minus F of n minus 2. So the first few values for F of n generated from this definition are here: 4, 7, 4, 4, 7, 10, 4, 4, 10, 13, 7, etc., etc., etc. If we continue that a bit further, we get this picture here. How are these values actually computed? Well, to see that, we can make kind of an evaluation graph in which we show how each value, F of n, is computed from ones with smaller values of n, here starting from F of 20. So the gray nodes at the bottom here represent initial conditions, places where F of n was sampled for n less than or equal to 0. Remember, that was a condition that we gave at the beginning of the definition. So the two different colors of edges correspond to the two different computations done in evaluating each F of n. So the inner one is shown red, the outer one is shown blue. So the inner one is the red lines there, the outer F evaluation is the blue lines there. So if we continue to F of 30, we get this pattern here. But what's the structure of this graph? If we pull out just the red graph on its own, we see it breaks into two path graphs that consist of the sequences of the F of n for odd and even n respectively. The blue graph, on the other hand, breaks into four components, each always a tree, leading respectively to the four different initial conditions. F of 0 is 1, F of minus 1 is 1, etc. And for example, we can now plot the actual values of F of n, showing which tree F of n for that particular n ends up being associated with. And so that's the picture of that there. So we'll be using the same basic setup throughout, though for different functions. We'll mostly consider recursive functions with a single term, i.e. with a single outermost f, not two, as happens in Fibonacci recurrences. So these are specific families of functions. We'll be focusing on the plus-like ones, the times-like ones, the subtract-like ones. We're calling them P, T, and S functions, and they have different forms, and they have different asymptotic behavior. Some of them probe only a finite number of initial conditions. Some of them probe an infinite number of initial conditions. So with this designation, the function we were just looking at is P312. Okay, let's take a closer look at P312. So let's start off by looking in more detail at what it does up to, for example, n equals 500. So there it is. So might seem like it's going to go on being kind of seemingly random forever, but something screen here. There we go. You might think it's going to go on kind of seemingly random like this forever, but if we take it further, we get a surprise. It seems to it seems to kind of resolve itself to something potentially simpler. So what's going on? Let's plot this again, but now showing which blue graph tree, remember that was the outer F, each value is associated with. So there's the result. Now what we see is that F of -3 and -2 trees, which are the last two colors there, they stop contributing to F of n when n is respectively 537 and 296. And these trees are finite and have sizes 53 and 15. Here are those trees. And the overall structure of the remaining trees, so here shown up to F of 5,000, eventually start to exhibit some regularity. And that's, and we can kind of home in on the regularity by arranging the trees in layers, starting from the root and then plotting just the number of nodes in each successive layer. So there we see that. So looking at these pictures suggests that there should be some kind of more or less direct formula for F of n, at least for large n. They also suggest that such a formula should have some kind of mod 6 type structure. And yes, there does turn out to be essentially a formula, though the formula is quite complicated and reminiscent of several other strangely messy formulas in other Ruliological cases, like as a Turing machine 600720 that I talked about in New Kind of Science, or the combinator expression that you get from a combination of what is it, 7 carefully arranged S's. And later on, we'll see that the much simpler recursive function P111, that's just F of n, is 1 plus F of n minus F of n minus 1, also does this kind of thing. And in fact, that P111 function, the values for that function form a sequence in which the successive blocks of length k have value k. So P312 has the same kind of structure, but much embellished. First, it has 6 separate riffled mod subsequences. Each subsequence then consists of a sequence of blocks. Given a value of n, we can compute, using this rather exotic formula, which subsequence that value of n is on. So which block for that subsequence it's in and where it is within that block. So we're kind of giving this sort of set of coordinates for what that value of n, how that value of n is interpreted by this nestedly recursive function. And it's, and you can see it's pretty exotic. 1876, it's not yards in a mile. It's some number that just shows up here as one tries to figure out how these functions work. Well, if we're using this complicated indices function to decode the sort of the mod, the block, the offset, we can see here, this is the kind of map that shows the different values of n, how things are decomposed by that function into the mod, the block, the offset. And given that, we can then, we realize that, for example, f of n equals 1,000, we're still not yet in the simple regime, so we can't describe our sequence in any simple way. But, and the indices calculation is meaningless with block -2 and so on. But for n equals 2,000, it happens that we're at block 0 for the mod 1 subsequence. And the way things are set up, we just start by giving exactly the form of block 0 for each mod. So for mod 1, this is the block, and this is the block that we're indexing in to get the actual values of the function. So now for n equals 2,000, we have offset 16 within this block. So the final value of f of 2,000 is simply the 16th value in this list, which happens to be 100. F of 2001 is then simply the next element within this block, or in this particular case, 109, and so on until we reach the end of the block. But what if we're not dealing with block 0? For example, according to the table that we just were looking at here, f of 3000 is determined by mod 3 block 1. Well, it turns out there's a straightforward, if messy, way to compute for any block B mod M, for mod M. And that's what it is. And we can just use this way of computing to compute the value of, say, f of 3000, effectively just by essentially evaluating a formula. Value of f of indices of 3000 is just 136. We don't have to follow through all the steps in the computation of the function. We can just use this kind of pseudo formula to work out the result. So what's particularly notable here is that this evaluation doesn't involve any recursion. In other words, at the cost of messiness, we've somewhat surprisingly been able to unravel all the recursion in P312 to arrive at a direct formula for the value of f of n for any n. So what else can we see about the behavior of f of n for P312? One notable feature is its overall growth rate. For large n, it turns out that as one can see by substituting this form into the recursive definition and just taking a limit, one can determine that f of n is about square root of 6n. And you can see the fit there. It's a fine fit, the red line. So one thing this means is that our evaluation graph, eventually that's the graph of sort of how the evaluations, how f of n depended on f of smaller values of n, that evaluation graph eventually has a roughly conical form. And this can be compared to the very regular cone that we get from P111, which has asymptotic values square root of 2n. There's that very regular cone from P111. So if one just looks at the form of the recursive definition for P312, it's far from obvious how far back that definition will need to probe. Or in other words, what values of f of n one will need to specify as initial conditions. As it turns out, though, the only values that are needed are f of minus 3, f of minus 2, f of minus 1, and f of 0. How can one see this? So in the expression 3 plus f of n minus f of n minus 2, it's only the outer f that can probe far back values. But how far it actually goes back depends on how much larger f of n minus 2 gets compared to n. So plotting f of n minus 2 and n together, we have this. And the point is that only for very few values of n does f of n minus 2 exceed n. And those are the values that probe back, because those are the values that sample n minus f of n minus 2. So meanwhile, for larger n, there can never be additional lookbacks, because f of n grows like square root of 6n, and that means that it will never exceed the n value. It will never be, if it's like n minus f of n minus 2, that's like n minus square root of n. So that will never end up being negative for sufficiently large n. So does any P312 recursion always have the same lookback? So far, we've considered specifically the initial condition f of n equals 1 for all n less than or equal to 0. But what if we change the value of f of 0? So here are some plots for different cases, changing the value of f of 0 and f of negative values. So we can see that all sorts of different things happen. So with f of 0 equals z, let's say, the look back goes to minus z for z greater than or equal to 3, and to z minus 4 for z between 1 and 2, z equal 1 and 2. So if z is less than or equal to 0, the function f of n is basically not defined, because the recursion is trying to compute f of n from f of n, or f of n plus 1, and so on. So it never makes progress. So the case f of 0 equals 2, i.e. z equals 2, is the one that involves the least look back and a total of 3 initial values. So that's how that works. And this is the evaluation graph. It's just going down to the initial values f of 0 equals 2. In this case, f of minus 1 is 1, f of minus 2 is 1. So by comparison, here's the evaluation graph for f of 0 equals 5, and that involves 6 initial values. So if we plot the value of f of n as a function of the value of f of 0, is what we get. For n less than 3, n is less than 3 times f of 0, so kind of the line across this picture, f of n always has simple behavior and is essentially periodic. That's what those vertical stripes are doing in this picture. And it's actually periodic with period 3. Those are the values. And it turns out that for any specified initial configuration of values, there is always only bounded lookback, with the bound apparently being determined by the largest of the initial values. That's f of n sub init. So what about the behavior of f of n for large n? Just like in our original f of 0 equals 1 case, we can construct those sort of blue graph trees of the outer f's rooted at each of the initial conditions. In the case f of 0 equals 1, we found that of the 4 trees, only 2 continue to grow as n increases. As we vary f of 0, the number of surviving trees varies quite erratically. So that this is plotting the number of surviving trees as a function of f of 0. So what about if we, instead of changing f of 0 and keeping all the other f of minus k equal to 1, we set f of n equals s, let's say, for all n less than or equal to 0. The result is somewhat surprising. For s greater than 2, the behavior turns out to be simple and similar to the behavior that we got for P111. So what can P312 be made to do if we change its initial conditions? With f of n equals 2 for n less than 0, we see that for small f of 0, the behavior remains tame, but for larger f, but as f of 0 increases, it starts showing increasing complexity. So this is the case where f of n equals 2 for all those very negative values, but then we set f of 0 separately, and this is showing what happens as when initial conditions where we're changing f of 0, but leaving f of negative numbers always equal to 2. So one question to ask is, what set of values f of n takes on? Given that the initial values have certain residues mod 3, all subsequent values must have the same residues. But apart from this constraint, it seems that all values for f of n are obtained, which is not surprising given that f of n grows only like square root of n. So it kind of gets to bounce around within the values that it can get to. All right, let's move on here. Let's talk about the P family. That is, of which P312 is an example. That's recursions of the form f of n is equal to a plus f of n minus b times f of n minus c. So P312 is just one example of this P family defined this way. And here's the behavior of some other P, ABC type sequences. And here are the evaluation graphs for those sequences, those recursive definitions. P312 is the first kind of seriously complex example. P111 has a particularly simple form that's shown right here, which turns out to correspond to the very simple formula given just in terms of a floor of a square root. So, and the evaluation graph in this case is just this here. Only a single initial condition, f of 0 equals 1, is used, and there's only a single blue graph tree with a simple form like this. So another interesting case is P123. That's the sequence we get for P123. And picking out only odd values of n, this is what we get. It might look just like the behavior of P111, but it's not. The lengths of the successive plateaus are now given like this, with differences that are these. Turns out this is exactly a nested sequence generated by joining together successive steps in the evolution of this substitution system here. So P123 immediately gets into its final behavior, even for small n. But as we saw rather dramatically with P312, there can be transient behavior that doesn't resolve until n is large. So a smaller case of this phenomenon occurs with P213. Above n equals 68, it shows simple square root pattern of behavior, basically like P111, but for smaller n, it's a bit more complicated. And in this case, the transients aren't due to blue graph trees that stop growing. Instead, there are only two trees associated with f of 0 and f of minus 1, but both of them soon end up growing in very regular ways. Okay, let's go on. Let's talk about the T family. That's f of n is, here, I'll show you. That's the form of the T family. This is the case where the outermost operation is not addition, but is times. That's why it's called the T family, or multiplication. Okay. Well, so here are some examples of behavior one gets for this T family. In each case, we're plotting on a log scale, and we're not including the T1 blank blank cases, which are always trivial. So we see that some sequences have very regular and readily predictable behavior, others do not. And this is reflected in the evaluation graphs for these functions. The first complicated case is T212. That's this behavior here. The evaluation graph for f of 50, I can show you. I just want to look at this for a second. Look at how simple that function is. 2 times f of n minus f of n minus 2. And look at how complicated its behavior appears. This is like quintessential kind of fair for the computational universe. Anyway, the evaluation graph for f of 50 in this case looks like this. And there's something that is immediately notable is in addition to looking back to the values f of 0 and f of minus 1, it also looks back to f of minus 24. Meanwhile, the evaluation graph for f of 51 looks back not only to f of 0 and f of minus 1, but also to f of minus 3 and f of minus 27. How far back does it look in general? Here's a plot showing which lookbacks are made as a function of n, with the roots of the blue graph trees being highlighted. So this is showing what, as a function of n on the x-axis, this shows what on the y-axis, what initial value it looks back to. So there's some alternation between behaviors for even and odd n, but apart from that, additional lookbacks are just steadily added as n increases. And indeed, the total number of lookbacks follows this simple pattern. But just for once, if one looks in more detail, it's not so simple. The lengths of the successive blocks are these. And so the lookbacks are quite unpredictable. But the main point here is that unlike for the P family, the number of lookbacks isn't limited. In a sense, to compute T212 for progressively larger n, progressively more information about its initial conditions is needed. When one deals with ordinary unnested recurrence relations, one's always dealing with a fixed lookback. And the number of initial conditions then just depends on the lookback. So for example, the Fibonacci recurrence has lookback 2, so it needs 2 initial conditions, while the standard factorial recurrence has lookback 1, so it needs only 1 initial condition. But for the nested recurrence relation T212, we see that this is no longer true. There can be an unboundedly large lookback. Okay, but let's look back at the actual T212 sequence. Here it is up to larger values of n. Or plotting each point as a dot looks like this. So given the recursive definition of f of n, the values of f of n must always be powers of 2. So this shows where each successive power of 2 is first reached as a function of n. Meanwhile, this shows the accumulated average of log to the base 2 of f of n as a function of n. So this is very well fit by just 0.38 times log n, implying that at least with this averaging, f of n asymptotically approximates n to the 0.26. And yes, it's somewhat surprising that what seems like a very exponential recursive definition should lead to an f of n that increases only like a power. But needless to say, this is the kind of surprise one has to expect in the computational universe. It's worth noticing that f of n fluctuates very intensely as a function of n. The overall distribution of values is very close to exponentially distributed. For example, with the distribution of logarithmic values of f of n for n between 9 million and 10 million looking like this. What can we say about this whole sequence? Let's say we reduce mod 2, the powers of 2 for each f of n, then we get a sequence which starts like this. It's definitely not uniformly random, but if one looks at blocks of sequential values, one can plot at which n each of the 2 to the b possible configurations of a length b block first appears. And eventually it seems as if all length b blocks for any given b will appear. By the way, whereas in the P family, there were always a limited number of blue graph trees associated with a limited number of initial conditions, for T212, the number of such trees increases with n as more initial conditions are used. So for example, here are the trees for f of 50 and f of 51. That's f of 50, and that's, oops, I think we don't have f of 51 here. But there'll be more trees for f of 51. So far, we've discussed T212 only with the initial condition f of n equals 1 or n less than or equal to 0. The fact that f of n is always a power of 2 relies on every initial value also being a power of 2. But here's what happens, for example, if f of n equals 2 to the s for n less than or equal to 0. So in general, one could think of T212 as transforming an ultimately infinite sequence of initial conditions into an infinite sequence of function values with different forms of initial conditions, potentially giving very different sequences of function values. So these are for different choices of our initial values. So note that for all choices of initial conditions, not all choices of initial conditions are possible. Some lead to situations like f of n being given in terms of f of n, or f of n being given in terms of only of f of n plus 1, where the evaluation of the function just can't make progress. All right, let's talk about the summer school sequence, T311. That's f of n equals 3 times f of n minus f of n minus 1. This was the sequence that we came up with at the 2003 summer school. So, well, we explored okay, here's the basic behavior of the T311 sequence that we found at the summer school. And here's its evaluation graph, which immediately reveals a lot more look back than happened in T212. So plotting the lookbacks as a function of n, this is what we get. Well, much as with T212, the total number of lookbacks varies with n in a fairly simple way. In this case, it's about 0.44 times n. So continuing the T311 sequence further, that's how the number of lookbacks varies. If we continue the T311 sequence further, it looks qualitatively very much like T212. And indeed, T311, despite its larger number of lookbacks, seems to behave basically just like T212. In a story typical of the principle of computational equivalence, T212 already seems to have filled out the computational possibilities. So T311 doesn't really have anything to add. All right, let's talk about the S family. So they're defined like this. F of n is n minus f of n minus a minus b. And we'll look at this as another somewhat historically motivated example of nestedly recursive functions defined this way. So let's start with a very minimal case we can call S1 0 or just S1. And so our standard initial condition, f of n equals 1 for n less than or equal to 0, doesn't work here because it implies that f of 1 equals 1 minus f of 1. But if we take f of n equal to 1 for n less than or equal to 1, we get the following behavior here. Meanwhile, with f of n equals 1 for n less than or equal to 3, as opposed to n less than or equal to 1, we get this kind of behavior. Well, the first obvious feature of both of these results is their overall slope, which turns out to be about 1 over phi, where phi is the golden ratio, 1 over phi is about 0.618. Not too hard to see why one gets this slope. Assume that for large n, we can take f of n equals sigma times n, then substitute this form into both sides of the recursive definition for the S family to get basically sigma times n is n minus sigma times n minus a minus b. So for large n, all that survives is the condition for the coefficients of n to be, which is this, sigma equals 1 minus sigma squared, which has solution sigma equals 1 over phi. So plotting f of n minus n over phi to kind of detrend it, for the case f of n equals 1, for n less than or equal to 1, we get this. And the evaluation graph in this case has a fairly simple form, as we can see even more clearly with a different graph layout. It's notable that only the initial condition f of 1 equals 1 is used, leading to a single blue graph tree that turns out to have a very simple kind of Fibonacci tree form, which, as we'll discuss below, as this has been known since the 1970s. Well, from this it follows that f of n is related to the Fibonacci-like substitution system that's given like this. In fact, the sequence of values for f of n can be computed just in this way, as an accumulation of substitution system results. And it turns out that in this case, f of n is just given exactly by the floor of n plus 1 divided by golden ratio. So what about when f of n equals 1, not just for n equals less than or equal to 1, but beyond? For n less than or equal to 2, the results are essentially the same as for n less than or equal to 1. But for n less than or equal to 3, that means that f of 1 equals 1, f of 2 equals 1, f of 3 equals 1. There's a surprise. The behavior is considerably more complicated. So let's just plot f of n minus n over phi, and we do it at different scales here, and we can see this kind of behavior. So looking at the evaluation graph in this case, we can see that the only initial conditions sampled are f of 1 equals 1 and f of 3 equals 1, with f of 2 only being reached if one specifically starts with f of 2. That's a piece of the evaluation graph in this case. Continuing the evaluation graph, we see kind of a mixture of irregularity and comparative regularity. So the plot of f of n has a sort of strange, that was this picture here, has a sort of strange hand-drawn appearance with overall regularity but detailed apparent randomness. The most obvious large-scale feature is bursting behavior, interspersed in audio. If you played this in audio, maybe we can do that, with an annoying hum that comes from those little wiggles, that systematic wiggles that you see before the bursts. So the bursts all seem to have approximately, not exactly the same structure, and get systematically larger. The lengths of successive regions of calm between bursts, characterized by runs with, let's say, f of n abs of f of n minus n over phi being less than 3, seem to consistently increase by a factor of phi. So what happens to S1 with other initial conditions? Here are a few examples. So how does, that's what happens with S1. How does SA depend on A? That's the coefficient in the first coefficient in the original definition. Well, sometimes there's at least a certain amount of clear regularity. Sometimes it's more complicated. As is very common, adding the parameter b in the definition doesn't seem to lead to fundamentally new behavior, though for b greater than 0, the initial condition f of n equals 1 and less than equal to 0 can be used, and that's the result that we get. So in all cases, only a limited number of initial conditions are sampled, bounded by the value of a plus b in the original definition. But as we can see, the behavior can either be quite simple or can be highly complex. What about more complicated rules? So highly complex behavior arises even from very simple rules. It's a phenomenon one sees all over the computational universe. And we're seeing it here in nestedly recursive functions. But if we make the rules, i.e. definitions for our functions, more complicated, will we see fundamentally different behavior or just more of the same? The principle of computational equivalence, as well as many empirical observations of other systems, suggests that it'll be just sort of more of the same. That once one's passed a fairly low threshold, the computational sophistication and complexity of behavior will no longer change. And indeed, this is what one sees in nestedly recursive functions. But below the threshold, different kinds of things can happen with different kinds of rules. There are several directions in which one can make rules more complicated. One that we won't discuss here is to use operations that go beyond arithmetic, like conditional ones or bitwise operations or whatever. Others tend to involve adding more instances of f in our definitions. An obvious way to do this is to take f of n to be given by a sum of terms in kind of Fibonacci style. There are very specific forms we can consider. As a first example that we can call f sub 3 ab, you can look at something like this. So the value of a doesn't seem to matter much, but changing b, we see this kind of behavior. So f312 has unbounded look back, at least starting with f of n equals 1 for n less than or equal to 0. But for larger b, f sub 3 1b has bounded look back. In both f sub 313 and f sub 315, there is continuing large-scale structure that we can see in these log plots, though this doesn't seem to be reflected in the corresponding evaluation graphs. As another level of Fibonacci-style definition, we can consider f sub 4 ab. That's given by something like this, but the 4 specified the sub 4, f sub 4, the 4 means there are 4 parameters. But the typical behavior here does not seem much different from what we already saw with the one-term definitions involving only 2 f's. So these are the f sub 4 definitions. So we note that f sub 4a is equivalent to s sub 2a. So cases like f sub 413 lead after a transient to prior exponential growth. So a somewhat more unusual case is what we can call g sub 3 abc. That's this function here. So if we kind of subtract overall trends, this is the behavior we get from that function. So for g sub 3 111, using initial conditions f of 1 equals f of 2 equals 1, and plotting f of n minus n over 2, we get this form here, which has a nested structure that's closely related to the result of concatenating binary sequences of successive integers, kind of a Champernowne number type thing. But despite the regularity in the sequence of values, the evaluation graph for this function is not particularly simple. So how else might we come up with more complicated rules? One possibility is that instead of adding f's by adding terms, we can add f's by additional nesting. So for example, we can consider what we can call s sub 3 of 1, f sub 3 1, here shown with initial condition f of n equals 1 for n less than or equal to 3. So here it is. That's a triply nested f. So we can estimate the overall slope here by solving for x in x equals 1 minus x cubed, and we get x is about 0.682. So subtracting this off, we get these forms here. Remarkably complicated. We can also consider deeper nestings. At depth d, the slope is the solution to x equals 1 minus x to the d. And somewhat remarkably, in all cases, the only initial conditions probed are f of 1 equals 1 and f of 3 equals 1. So as another example of higher nesting, we can consider the class of functions that we'll call n sub 3a. That's the form of those functions, where the second term is a doubly nested form. So subtracting a constant 1 over phi, 1 over golden ratio slope, we get this kind of behavior here. Again, the evaluation graph for n sub 3, 1 is complicated, but it has some definite structure, even if it looks a bit like a fish in this particular rendering. So, well, what happens if we nest even more deeply, say defining n sub 4a functions, so something like this? With depth D nesting, we can estimate the overall slope of f of m by solving for x in x equals 1 minus x times 1 minus x to the d, and that's just a polynomial of the form. That's the polynomial we're solving for, so that for d equals 3, case here, the overall slope is the real root of x cubed plus x squared plus x equals 1, or about 0.544. So subtracting out this overall slope, we get these forms here. And yes, the sine curve-like form of n sub 4, 5 is very odd. Well, continuing 10 times longer, though, so that's, look at that sort of strange sine curve of bottom left, n sub 4, 5. If we continue 10 times longer, though, things are indeed sort of squaring off. What happens if we continue nesting deeper? N sub d of 1 stays fairly tame. However, N sub d2 already allows for more complicated behavior. And for different values of a, there are definite regularities. Here are examples for 5, for a being 5. So it's just remarkable that one can have a rule, a function that is defined in such a simple way, and yet it produces such diverse, complicated behavior. But anyway, there are all sorts of other extensions and generalizations one might consider. Some involve alternate functional forms, others involve introducing additional functions or allowing multiple arguments to our function f. Okay, let me do an aside here about the continuous case. So in talking about recursive functions f of m, we've been assuming, as one normally does, that n is always an integer. But can we generalize what we're doing to functions f of x, where x is a continuous real number? So consider, for example, the continuous analog of the Fibonacci recurrence. This produces kind of a staircase-like function whose steps correspond to the usual Fibonacci numbers. But if we adjust the initial condition, we get a slightly different result. This is now an initial condition where f of x equals x when x is less than or equal to 2. Well, we can think of these as being solutions to a kind of Fibonacci delay equation where we've given initial conditions not at discrete points, but instead on an interval. So what happens with nestedly recursive functions? We can define an analog of S1 like this, and plotting this along with the discrete result, the continuous result over on the left, we get this. So in more detail, we get for the continuous result something like this, where the plateaus occur at the so-called Witoff numbers given by floor of golden ratio times k. So changing the initial condition to be x is less than or equal to be, well, it should be equal to 1, I guess, for x less than or equal to 3, we get these forms here. You can see that we have that constant value 1 over on the left for, that's a continuous case on the left, for x less than or equal to 3, and then those are the results we get. So removing the overall slope by subtracting x over phi, we get this form here. So one feature of the continuous case is that one can continuously change initial conditions, though the behavior one gets typically breaks into domains with discontinuous boundaries. As in this case where we're plotting the value of f of x as a function of x along the x-axis and as a function of the cutoff x in the initial conditions for f of x where we're saying that f of x is equal to x for x less than or equal to 0. Sorry, x less than or equal to x0. Now we're plotting x0 on the y-axis here. So what about other rules? A rule like P312, given constant initial conditions, effectively just copies and translates the initial interval and gives a simple order 0 interpolation of the discrete case. With initial condition f of x equals x, some segments get tipped, but otherwise it's pretty straightforward. So all the cases we've considered here don't look back to negative values in either the discrete or continuous case. But what about a rule like T212 that progressively looks back further? With the initial condition f of x equals 1 for x less than or equal to 0, one gets the same result as in the discrete case. But if one uses the initial condition f of x is abs of x minus 1 for x less than or equal to 0, and the abs of x minus 1 is needed to avoid ending up with f of x depending on f of y or y greater than x, one instead has this form here. So this is what we're looking at. If x is less than or equal to 0, then the result is abs of x minus 1. Otherwise, it's 2f of x minus f of x minus 2. So this gives a rather different result. That's what it looks like. Continuing for larger x on a log scale, this is what we get. So successively zooming in on one of the first regions of noise, we see that it ultimately consists just of a large number of straight segments. So this is now looking, zooming in by factors of 10 on a place where there's sort of that initial noise. So what's going on here? If we count the number of initial conditions that are used for different values of x, we see that it has discontinuous changes, and that's what leads to disjoint segments in f of x. So that's the number of initial conditions used for a given x value to evaluate f of x for a certain specific value of x. We use some discrete number of initial conditions. Plotting that discrete number of initial conditions, it jumps as you change x. So plotting over a larger range of x values, the number of initial conditions used looks something like this. And plotting the actual values of those initial conditions, we get this weird-looking curve. So if we go on, more intense regions, we go to later, sort of more intense regions of noise, we see more fragmentation. And presumably in the limit x goes to infinity, we get an analog of an essential singularity in f of x. Well, I mean, I find it completely remarkable that, and I'd never seen anything like this, that these continuous recursion relations lead to behavior that's like this. But anyway, for the S family with its overall n over phi trend, even constant initial conditions, say for S1, already lead to tipping, here shown sort of compared to the discrete case. And that's just another example of this, and one could go on and study these other nestedly recursive functions for continuous values x. And I think there's all kinds of interesting mathematics to do there. I just scratched the surface of that. All right, how do you actually compute recursive functions? Let's say we have a recursive function like the standard Fibonacci one. How do we actually use this to compute the value of, say, f of 7? Well, we can start from f of 7, then use the definition to write this as f of 6 plus f of 5, then write f of 6 as f of 5 plus f of 4, and so on. And we can represent this using an evaluation graph in this form here. But this computation is, in a sense, very wasteful. For example, it's independently computing f of 3 5 separate times, and of course getting the same answer each time. But what if we just stored each f of n as soon as we compute it, and then retrieve the stored cached value whenever we need it again? In the Wolfram language, it's a very simple change to our original definition. Here it is. Now the evaluation graph in this case becomes much simpler when we're now caching values. And indeed, it's this kind of minimal evaluation graph that we've been using in everything we've discussed so far. We've merged identical values in everything we've discussed so far. What's the relationship between the tree evaluation graph and this minimal one? The tree graph is basically an unrolled version of the minimal graph in which all possible paths that can be taken from the root node to the initial condition nodes have been treed out. In general, the number of edges that come out of a single node in an evaluation graph will be equal to the number of instances of the function f that appear on the right-hand side of the recursive definition we're using. So 2 in the case of the standard Fibonacci definition. So this means that if the maximum length of path from the root to the initial conditions is s, the maximum number of nodes that can appear in the unrolled graph is 2 to the s. And whenever there are a fixed set of initial conditions, i.e. if there's always the same look back, the maximum path length is essentially n, implying that in the end, the maximum number of possible nodes in the unrolled graph will be 2 to the n. So in the actual case of the Fibonacci recurrence, the number of nodes in the unrolled graph is 5 to the n, or about 1.6 to the n. But if we actually evaluate f of 7, say in the Wolfram language, what is the sequence of f of n's that we'll end up computing? Or in effect, how will the evaluation graph be traversed? So here are the results for the unrolled and minimal evaluation graphs, that is with and without caching and with caching. These are showing in the process of evaluation what value of n is being computed. At the first evaluation, it's 7, et cetera, et cetera, et cetera. By the time we get to the 30th evaluation, it looks like it's evaluating f of 1. The 31st is evaluating f of 0, and so on, in the uncached case. So particularly in the first case, this isn't the only conceivable result we could have gotten. It's the way it is here because of the particular leftmost innermost evaluation order that the Wolfram language uses by default. In effect, we're traversing the graph in a depth-first way, the evaluation graph, that is, in a depth-first way. In principle, we could use other traversal orders, leading to f of n's being evaluated in different orders. But unless we allow other operations, like f of 3 plus f of 3 goes to 2 times f of 3, to be interspersed with f evaluations, we'll always end up with the same number of f evaluations for any given evaluation graph. But for a given evaluation graph. But what is the correct evaluation graph? The unrolled one or the minimal one? Well, it depends on the computational primitives we're prepared to use. With a pure stack machine, the unrolled graph is the only possible one. But if we allow random access memory, then the minimal graph becomes possible. Okay, so what happens with nestedly recursive functions? Here, for example, are the unrolled and minimal graphs for T212. And here are the sequences of f of n's that are computed. So on the left, it's without caching. On the right, it's with caching. And here's a comparison of the number of nodes, i.e. the number of f evaluations, from the unrolled and minimal evaluation graphs. So clearly with the minimal graph, where we're doing caching, we have to do a lot less evaluations. This is on a log scale. So it's roughly 1.2 to the n for the unrolled case versus 0.5 n linear for the other case. So different recursive functions lead to different patterns of behavior. The differences are less obvious in evaluation graphs, but can be quite obvious in the actual sequence of f of n's that are evaluated. So here's some T212 for a couple of different initial conditions. But although looking at evaluation sequences from unrolled evaluation graphs can be helpful as a way of classifying behavior, the exponentially more steps involved in the unrolled graph typically make it impractical in practice. Okay, primitive recursive or not. Recursive functions have a fairly long history that we'll talk about soon, and for nearly 100 years, there's been a distinction made between primitive recursive functions and general recursive functions. Primitive recursive functions are basically ones where there's a know-in-advance pattern of computation that has to be done. General recursive functions are ones that may, in effect, make one have to search arbitrarily far to get what one needs. In Wolfram language terms, primitive recursive functions are roughly ones that can be constructed directly using functions like nest and fold, perhaps nested. General recursive functions can also involve functions like nest while and fold while. So, for example, the standard Fibonacci definition, the function f of n is primitive recursive and can be written, for example, in this form with a single nest. So lots of the functions that one encounters in practice are similarly primitive recursive, including most typical mathematical functions like plus or power or GCD or prime and so on. And for example, functions that give results of n steps in the evolution of a Turing machine, cellular automaton, or and so on, are also primitive recursive. But functions that, for example, test whether a Turing machine will ever halt or give the state that it achieves if and when it does halt are not, in general, primitive recursive. On the face of it, our nestedly recursive functions seem like they must be primitive recursive since they don't, for example, appear to be searching for anything. But things like the presence of longer and longer lookbacks raise questions. And then there's the potential confusion of the very first example, dating from the late 1920s, of a recursively defined function known not to be primitive recursive, the Ackermann function. The Ackermann function has 3 or sometimes 2 arguments, and notably its definition, which is here given in sort of classic form, includes nested recursion. So this is what the evaluation graphs look like for some small cases of the Ackermann function. And so we can just look at the form of the Ackermann function in more, we can sort of unroll it for specific initial values, f of 0, f of 1, f of 2, and so on. Something got left out here. Oops. Well, at least in this form, f of mxy involves m nestings. But a given primitive recursive function can only involve a fixed number of nestings. It might be conceivable that we could rewrite f of mxy in certain cases to involve only a fixed number of nestings. But if we look at f of mmm, then this turns out to inevitably grow too rapidly to be represented by a fixed number of nestings, and thus cannot be primitive recursive. But it turns out that the fact this can happen depends critically on the Ackermann function, that's the function we've just been talking about, having more than one argument, so that one can construct the kind of diagonal like f of mmm. So what about our nestedly recursive functions? Well, at least in the form that we've used them, they can all be written in terms of fold. The key idea is to accumulate a list of values so far, conveniently represented as an association, sampling whichever parts are needed, and then at the end, taking the last element. So for example, the summer school function, this one here, can be written in this form here, with just a fold. So an important feature here is that we're getting lookup, the function lookup, to give 1 if the value it's trying to look up hasn't been filled in yet, implementing the fact that f of n equals 1 for any n less than or equal to 0. So yes, our recursive definition might look back further and further, but it always just finds value 1, which is easy for us to represent without, for example, any extra nesting. Well, the ultimate historical definition of primitive recursion, though, doesn't involve subsets of the Wolfram language. The definition was given almost exactly 100 years too early. Instead, it involves a specific set of simple primitives. And that's these things here, the 0 primitive, the successor primitive, the projection primitive, the composition primitive, and the recursion primitive. There is an alternative equivalent definition for recursion. Notice the recursion here given with pattern matching. We can do it explicitly. I don't have the form. We can also give it explicitly in terms of fold if we want to. So can our nestedly recursive functions be written purely in terms of these classic primitive recursive primitives? The answer is yes, though it's seriously complicated. A simple function like plus can, for example, I don't think we're giving this form, okay, you can write plus as r of p1 comma s, so that we can compute plus just by applying that function r p1 of s to 2 and 3, that gives 5. times being written of R of Z of C plus P1, P3, and so on. And factorial can be written in some similarly simple form, but even Fibonacci, for example, seems to require a very much longer specification. In writing kind of primitive recursive style definitions of Wolfram language, we accumulated in lists and associations, values in lists and associations. But in the ultimate definition of primitive recursion, there are no such constructs. The only form of data is positive integers. But for our definitions of nestedly recursive functions, we can use a tupling function that packages up any integer list of integer values into a single integer and an untupling function that unpacks it. And we can do this, say, based on a two-element tupling, a pairing function that works like this. So this is taking pairs of integers and writing like the pair of integers 5, 3 is just encoded as 28, or the pair of integers 2, 5 is encoded as 33. We're encoding pairs of integers as single integers. What about the actual if n is less than or equal to 1, 0 then 1 look-back test? Well, if can be written in primitive recursive form too. For example, I don't have that form, unfortunately. So there's a form that's fairly short, R of C of S, Z, C of F of C of S of P2 of n, which is equivalent to if n is less than or equal to 0, 1, otherwise f of n. So our nestedly recursive functions, as we're using them, are indeed primitive recursive. And more strictly, finding values f of n is primitive recursive. Asking questions like, for what n does f of n reach 1,000 might not be primitive recursive. The obvious way of answering a question like that involves a fold-while style non-primitive recursive search, but proving that there's no primitive recursive way to answer the question is likely very much harder. By the way, it's worth commenting that while for primitive recursive functions, it's always possible to compute a value of f of n for any n, that's not necessarily true for general recursive functions. For example, if we asked for what n does f of n reach 1,000, there might simply be no answer to that. F of n might never reach 1,000. And when we look at the computations going on underneath, the key distinction is that in evaluating primitive recursive functions, the computations always halt, while for general recursive functions, they may not. So, okay, our nestedly recursive functions can be represented in an official primitive recursive form, but they're very complicated in that form. So that raises the question, what functions can be represented simply in this form? Well, in a new kind of science, I gave some examples, each minimal for the output it produces. And you can see there the simple primitive recursive form on the left, giving these various functions that are like 2 to the n, or the sawtooth, or 2 to the 2 to the n, and so on. A very diverse range of kinds of behaviors, all made from just putting together these primitive recursive elements. Well, then there's an interesting function I found, this guy here. It's the simplest primitive recursive function without any obvious regularity. Because it's primitive recursive, it's possible to express it in terms of functions like fold, though it's two layers deep in those, making it in some ways more complicated, at least in the so-called Grigorchek hierarchy that counts fold levels as concerned, than our nestedly recursive functions. Here's the form of that function as an explicit, the form of this function here as an explicitly written out in terms of folds. But there's still an issue to address with nestedly recursive functions and primitive recursion. When we have functions like T212 that reach back progressively further as n increases, there's a question of what they'll find. We've simply assumed f of n equals 1 for n less than or equal to 0, but what if there was something more complicated there? Even if f of minus n was given by some primitive recursive function, say p of m, it seems possible that in computing f of n, one could somehow end up bouncing back and forth between positive and negative arguments, and in effect searching for an m for which p of m has some particular value, and in doing that, searching, one could find oneself outside the domain of primitive recursive functions. And this raises yet another question. Are all definitions we can give of nestedly recursive functions consistent? Consider, for example, a definition like this. Now ask, what is f of 1? Well, we apply the recursive definition, but this gives us f of 1 is 1 minus f of 0, or f of 1 is 1 minus f of 1, or in other words, an inconsistency. There are many such inconsistencies that seem to happen instantly when we apply definitions, but it seems conceivable that there could be insidious inconsistencies that show up only after many applications of a recursive definition. And it's also conceivable that one could end up with loops, like f of I equals I, and things like this could be reasons that f of n might not be a total function defined for all n. Well, we've seen all sorts of complex behavior in nestedly recursive functions, and what the principle of computational equivalence suggests is that whenever one sees complex behavior, one must in some sense be dealing with computations that are as sophisticated as any computation can be. And in particular, one must be dealing with computations that can somehow support computation universality. So what would it mean for a nestedly recursive function to be universal? For a start, one would need some way to program the function. There seem to be a couple of possibilities. First, one could imagine packing both code and data into the argument n of f of n. So, for example, one might use some form of tupling function to take a description of a rule in an initial state for a Turing machine, together with the specification of a step number, then package all these things into an integer n that one feeds into one's universal nestedly recursive function f. Then the idea would be that the value computed for f of n could be decoded to give the state of the Turing machine at the specified step. So such a computation by definition always halts, but much as one computes with Turing machines by successively asking for the next step in their evolution, one can imagine setting up a harness that just keeps asking for values of f of n at an infinite progression of values n. So another possible approach to making a universal nestedly recursive function is to imagine feeding in a program through the initial conditions one gives to the function. There might well need to be decoding involved, but in some sense what one might hope is that just by changing its initial conditions, one could get a nestedly recursive function with a specific recursive definition to emulate a nestedly recursive function with any other recursive definition, or say, for a start, any linear recurrence. Perhaps one could construct a complicated nestedly recursive function that would have this property, but what the principle of computational equivalence suggests is that it should be possible to find the property even in naturally occurring cases like P312 or P2 or T212. The situation is probably going to be quite analogous to what happened with the Rule 110 cellular automaton or the two-state, three-color Turing machine 596440. By looking at the actual behavior of the system, one got some intuition about what was likely to be going on, and then later, with great effort, it became possible to actually prove computation universality. In the case of nestedly recursive functions, we've seen here examples of just how diverse the behavior generated by changing initial conditions can be. It's not clear how to harness this diversity to extract some form of universality, but it seems likely that the raw material is there, and that nestedly recursive functions will show themselves as able to join so many other systems in fitting into the framework defined by the principle of computational equivalence. Okay, let's talk about some history. Well, once one has the concept of functions and the concept of recursion, nestedly recursive functions aren't in some sense a complicated idea. And between kind of that fact and the fact that nestedly recursive functions haven't historically had a clear place in any major line of mathematical or other development, it's quite difficult to be sure one's accurately tracing their history. But I'll describe at least what I currently know. The concept of something like recursion is very old, closely related to mathematical induction, which was already being used for proofs by Euclid around 300 BC. And in a quite different vein, or around the same time, though not recorded in written form until many centuries later, Fibonacci numbers arose in Indian culture in connection with the enumeration of prosody. You know, how many different orders are there in which to say the Sanskrit words in this Veda? Then in 1202, Leonardo Fibonacci, at the end of his calculational math book Liber Abaci, which was notable for popularizing Hindu Arabic numerals in the West, stated, more or less as a recreational example, his rabbit problem in recursive form. and explicitly listed the Fibonacci numbers up to 377. But despite this early appearance, explicit recursively defined sequences remained largely a curiosity until as late as the latter part of the 20th century. So the concept of an abstract function began to emerge with calculus in the late 1600s and became more solidified in the 1700s, but basically always in the context of continuous arguments. A variety of specific examples of recurrence relations, for binomial coefficients, Bernoulli numbers, and so on, were in fairly widespread use. But there didn't seem yet to have yet been a sense that there was a general mathematical structure to study. In the course of the 1800s, there had been an increasing emphasis on rigor and abstraction in mathematics, leading by the latter part of the century to a serious effort to axiomatize concepts associated with numbers. Starting with concepts like the recursive definition of integers by repeated application of the successor operation, by the time of Peano's axioms for arithmetic in 1891, there was a clear general notion, particularly related to the induction axiom, that integer functions could be defined recursively. And when David Hilbert's program of axiomatizing mathematics got underway at the beginning of the 1900s, it was generally assumed that all integer functions of interest could actually be defined specifically using primitive recursion. The notation for recursively specifying functions gradually got cleaner, making it easier to explore more elaborate examples. And in 1927, Wilhelm Ackermann, a student of Hilbert's, introduced in completely modern notation a reasonable mathematical function that, as we discussed above, he showed was not primitive recursive. And if we look here at his paper, place here. A lot of stuff. There we go then. This is the paper from Wilhelm Ackermann, 1927. Right there, in this paper, without any particular comment, and is a nestedly recursive function definition from 1927. Well, in 1931, Kurt Gödel streamlined the representation of recursion and solidified the notion of general recursion. There soon developed a whole field of recursion theory, though most of it was concerned with general issues, not with specific, concrete recursive functions. A notable exception was the work of Rosa Peter, formerly Politzer, beginning in the 1930s, and leading in 1957 to her book, Recursive Functions, which contains a chapter on nested recursion, which I'm showing here. Whole chapter on nested recursion. But despite the many specific, mostly primitive recursive functions discussed in the rest of the book, this chapter doesn't stray far from the particular function Ackermann defined, or at least Peter's version of it. Well, what about the recreational mathematics literature? By the late 1800s, there were all sorts of publications involving numbers, games, and so on, that at least implicitly involved recursion. An example being Edward Lucas's 1883 Tower of Hanoi puzzle. But perhaps because problems tended to be stated in words rather than in mathematical notation, it doesn't seem as if nestedly recursive functions ever showed up. In the theoretical mathematics literature, a handful of somewhat abstract papers about nested recursion did appear, an example being one from 1961 by this is a nested recursion theoretical paper by William Tate, then at Stanford. But meanwhile, the general idea of recursion was slowly beginning to go from purely theoretical to more practical. John McCarthy, who had coined the term artificial intelligence, was designing Lisp as the language for AI, and by 1960 was writing papers with titles like Recursive Functions of Symbolic Expressions and Their Computation by Machine. In 1962, McCarthy came to Stanford to found the AI lab there, bringing with him enthusiasm for both AI and recursive functions. And by 1968, these two topics had come together in an effort to use sort of AI methods to prove properties of programs, and in particular programs involving recursive functions. And in doing this, John McCarthy came up with an example he intended to be awkward. That's exactly a nestedly recursive function. Well, in our notation, that function would look like this. It became known as McCarthy's 91 function because, yes, for many n, f of n equals 91. Well, these days it's trivial to evaluate this function and to find out that f of n equals 91 only up to n equals 102. But even given the evaluation, even the evaluation graph is somewhat large. And in pure recursive evaluation, the recursion stack can get deep, which back then was a struggle for Lisp systems to handle. There were efforts at theoretical analysis, for example, by Zohar Manor, who in 1974 published a book called A Mathematical Theory of Computation, which, in a section entitled Fixed Points of Functionals, presents the 91 function and other nestedly recursive functions, particularly in the context of evaluation order questions. So in the years that followed, a variety of nestedly recursive functions were considered in connection with proving theorems about programs and with practical assessments of Lisp systems, a notable example being Ikuo Takeuchi's 1978 triple recursive function. Oh, that's the graph for the 91 function. So this is Takeuchi's triple recursive function that John McCarthy called TAC. But in all these cases, the focus was on how these functions will be evaluated, not on what their behavior would be. And it was typically very, very simple behavior. But now we have to follow another thread in the story. Back in 1961, right on the Stanford campus, a then 16-year-old Douglas Hofstadter was being led towards nestedly recursive functions. As Doug tells it, it all started with him seeing that squares are interspersed with gaps of 1 or 2 between triangular numbers, and then noticing patterns in those gaps, and later realizing that they showed nesting. Meanwhile, at Stanford, he had access to a computer running Algol, a language which, like Lisp, and unlike Fortran, supported recursion, though this wasn't particularly advertised since recursion was still generally considered quite obscure. As Doug tells it, within a year or two, he was using Algol to do things like recursively create trees representing English sentences. Meanwhile, in a kind of imitation of the Elusist game, Guess a Card kind of game, Doug was apparently challenging his fellow students to a function game based on guessing a math function from specified values. And as he tells it, he found that functions that were defined recursively were the ones people found it hardest to guess. Well, that was all in the early 1960s, but it wasn't until the mid-1970s that Doug Hofstadter returned to such pursuits. After various adventures, Doug was back at Stanford writing what became his book, Gödelischer Bach. And in 1977, he sent a letter to Niels Sloan, creator of the 1973 Handbook of Integer Sequences, and what's now the Online Encyclopedia of Integer Sequences, or OEIS. Here's the letter. As suggested by the accumulation of sequence ID notations that are written on the right in the letter, Doug's eta sequences had actually been studied in number theory before. In fact, since at least the 1920s, they're now usually called beta sequences. But the letter went on, now introducing some related sequences that had nestedly recursive definitions. As Doug pointed out, these particular sequences, which were derived from golden ratio versions of his eta sequences, have a very regular form, which we would now call nested. And it was the properties of this form that Doug seemed most concerned about in the letter. But actually, as we saw above, just a small change in initial conditions in what I'm calling S1 would have led to much wilder behavior. But that apparently wasn't something Doug happened to notice. A bit later in the letter, though, there was another nestedly recursive sequence that Doug described as a horse of an entirely another color. The quotes, absolutely crazy in caps, Q sequence. Well, 2 years later, Doug's Gödel-Escherbach book was published, and in it, tucked away at the bottom of page 137, a few pages after a discussion of recursive definition of text, with examples such as the strange bagels that the purple cow without horns gobbled, there was the Q sequence. Strangely, though, there was no picture of it, and Doug listed only 17 terms, which until I was writing this was all I assumed he had computed. So now nestedly recursive functions were out in the open in what quickly became a very popular book. But I don't think many people noticed them there, though as I'll discuss, I happened to. Gödel-Escherbach is primarily a playful book focused on exposition, not the kind of place you'd expect to find a new kind of mathematical style result. Still, quite independent of the book, Neil Sloan showed Doug's 1977 letter to his Bell Labs colleague Ron Graham, who within a year made a small mention of the Q sequence in a staid academic math publication in a characteristic kind of stated as a problem Erdos form in this paper here. Well, there was a small sort of tight-knit circle of serious mathematicians, essentially all of whom, as it happens, I personally knew, who would chase these kinds of easy-to-state but hard-to-solve problems. Another was Richard Guy, who soon included the sequence as part of problem E31 in his Unsolved Problems in Number Theory, and mentioned it again a few years later. But for most of the 1980s, little was heard about the sequence. As it later turned out, a senior British applied mathematician named Brian Connolly, who wasn't part of the aforementioned tight-knit circle, had, presumably as a kind of hobby project, made some progress, and in 1986 had written to Guy about it. Guy apparently misplaced the letter, but later told Connolly that John Conway and Sol Golomb had worked on similar things. Conway presumably got the idea from Hofstadter's work, though he had a habit of obfuscating his sources. But in any case, on July 15th, 1988, Conway gave a talk at Bell Labs entitled Some Crazy Sequences. Notice the word crazy, just like in Hofstadter's letter to Sloan, in which Conway discussed the regular enough to be mathematically interesting sequence, which we're calling G sub 3 111 here, this one. Well, despite its physical regularity, Conway couldn't mathematically prove certain features of the wiggles in the sequence, and his talk offered a $10,000 prize for anyone who could. By August, a Bell Labs mathematician named Colin Mallows had done it. Conway claimed, later to be contradicted by video evidence, that he'd offered only $1,000, and somehow the whole affair landed as a story in the August 30th New York Times under the heading Intellectual Duel, Brash Challenge, Swift Response. But in any case, this particular nestedly recursive sequence became known as Conway's challenge sequence. So what about Sol Golomb? Turns out he'd started writing a paper, though he never finished it. And he'd computed 280 terms of the Q sequence. He wasn't much of a computer user, and noticed a few coincidences. But he also mentioned another kind of nestedly recursive function sequence, no doubt inspired by his work on feedback shift registers, a sequence like this. As he noted, the behavior depends greatly on the initial conditions, though it's always periodic. With his student Anjung Chen, he found long period examples. Okay, so by 1988, nestedly recursive functions had at least some notoriety. So what happened next? Not so much. There's a modest academic literature that's emerged over the last few decades, mostly concentrated very specifically around Conway's challenge sequence, Hofstadter's Q function, or very similar meta-Fibonacci generalizations of them. And so far as I know, even the first published large-scale picture of the Q sequence only appeared in 1998, though I had pictures of it years earlier. Why wasn't more done with nestedly recursive functions? At some level, it's because they tend to have too much computational irreducibility, making it pretty difficult to say much about them in traditional mathematical ways. But perhaps more important, studying them broadly is really a matter of ruliology. It requires the idea of rules and of expecting the kinds of behavior and phenomena that are characteristic of systems in the computational universe. And that's something that's still not nearly as widely understood as it should be. Well, let me talk about my personal story with nestedly recursive functions. I think 1979 was the year when I first sort of took recursion seriously. I'd heard about the Fibonacci sequence, though not under that name, as a young child many years earlier, and I implicitly and sometimes explicitly encountered recursion, though sometimes through error messages, in computer algebra systems I'd used. In science, I'd studied fractals quite extensively, Benoit Mandel's book having appeared in 1977, and I'd been exposed to things like iterative maps. And I'd quite extensively studied cascade processes, notably of quarks and gluons in QCD, which are also kind of a form of recursion. As I think about it now, I realize that for several years I'd written programs that made use of recursion, and I had quite a lot of exposure to Lisp and the culture around it. But it was in 1979, having just started using C, that I first remember writing a program for doing percolation theory, where I explicitly thought, this is using recursion. But then in late 1979, I began to design SMP, a symbolic manipulation program, the forerunner of the modern Wolfram language. And in doing this, I quickly solidified my knowledge of mathematical logic and the then fledgling field of theoretical computer science. My concept of repeated transformations for symbolic expressions, which is still the core of the Wolfram language today, is somehow fundamentally recursive. And by the time we had the first signs of life for our SMP system, Fibonacci was one of our very first tests. We soon tried the Ackermann function too. And in 1980, I became very interested in the problem of evaluation order, particularly for recursive functions. And the best treatment I found of it, though at the time it wasn't particularly useful to me, was in none other than the book by Zohar Manna that I mentioned before. In a strange twist, I was at that time, 1980, also studying gauge choices in physics. And it was only last year that I realized, in 2023, that is, that I realized that they're fundamentally the same thing as evaluation orders in function evaluation. Well, it was soon after it came out in 1979 that I first saw Doug Hofstadter's book. At the time, I wasn't too interested in its kind of Lewis Carroll-like aspects or its exposition. I just wanted to know what the science meat in it was. And somehow I found the page about the Q sequence and filed it away as something interesting. I'm not sure when I first implemented the Q sequence in SMP, but by the time we released version 1.0 in July 1981, well, here it was. It was an external package, hence the X prefix, for evaluating Hofstadter's recursive function. Elegant using memoization, with the description I gave saying, presumably because that's what I'd noticed, that its values have several properties of randomness. Notice the syntax of Wolfram language is a little bit cleaner than the syntax of SMP back in 1981. Well, firing up a copy of SMP today, oops, that's not what I thought. Oh dear. Let me try. Yeah, there we go. So firing up a copy of SMP today, running on a virtual machine that still thinks it's 1986, I can run this piece of code and easily compute the function. So there it is. I can even plot it, though without an emulator or a 1980s period storage tube display, only the ASCIIfied rendering works. So what did I make of this function back in 1981? I was interested in how complexity and randomness could occur in nature, but at the time I didn't have enough of a framework to understand the connection. And as it was, I was just starting to explore cellular automata, which seemed a lot more nature-like, which soon led me to things like Rule 30 and the phenomenon of computational irreducibility. Still, I didn't forget the Q sequence, and when I was building Mathematica, I used it again as a test. So here's an example. The .tq extension came from the brief period in 1987 when we were trying out technique as the name of our system, what will later become Wolfram language. When Mathematica 1.0 was released on June 23rd, 1988, the Q sequence appeared again, this time as an example in the soon in every major bookstore Mathematica book. I don't think I was aware of Conway's lecture that occurred just 18 days later. And for a couple of years, I was consumed with tending to a young product and a young company. But by 1991, I was getting ready to launch into basic science again. Meanwhile, the number theorist and today horologist Ilan Vardy, yet again from Stanford, had been working at Wolfram Research and writing a book entitled Computational Recreations in Mathematica, which included a long section on the analysis of Takeuchi's nested recursive function, TAC. So my email archive records an exchange that I had with Ilan Vardy at that time, about nestedly recursive functions. He suggested a more symmetrical nested recursive function. I responded, including a picture that I'd made that made it fairly clear that this particular function would have only nested behavior and not seem random. Well, by the summer of 1991, I was in the thick of exploring different kinds of systems with simple rules, discovering the remarkable complexity they could produce, and filling out what became Chapter 3 of a new kind of science. It's called The World of Simple Programs. Then came Chapter 4, Systems Based on Numbers. I'd known since the mid-1980s about the randomness in things like digit sequences produced by successive arithmetic operations. But what about randomness in pure sequences of integers? I resolved to find out just what it would take to produce randomness there. And so it was that on August 13th, 1993, I came to be enumerating possible symbolic forms for recursive functions and selecting ones that could generate at least 10 terms. As soon as I plotted the survivors, I could see that interesting things were going to happen. Was this complexity somehow going to end? I checked out to 10 million terms, and soon I started collecting my prized specimens and making a gallery of them. I had some one-term recurrences and some two-term ones. Somewhat short-sightedly, I was always using Fibonacci-like initial conditions, f of 1 equals f of 2 equals 1, and I rejected any recurrence that tried to look back to f of 0, f of minus 1, and so on. And at the time, with this constraint, I only found really interesting behavior in two-term recurrences. In 1994, I returned briefly to nestedly recursive sequences, adding a note, solving a few of them, and discussing evaluation graphs for some others. When I finally finished A New Kind of Science in 2002, I included a list of historical close approaches to its core discoveries, one of them being Douglas Hofstadter's work on recursive sequences. In retrospect, back in 1981, I should have been able to take the Q sequence and recognize it in it the essential Rule 30 phenomenon. But as it was, it took another decade and many other explorations in the computational universe for me to build up the right conceptual framework to see this. In A New Kind of Science, I studied many kinds of systems, probing them far enough, I hoped, to see their most important features. But recursive functions were an example where I always felt there was more to do. I felt I'd only just scratched the surface. In June 2003, a year after A New Kind of Science was published, we held our first summer school. And as a way to introduce methodology and to be sure that people knew I was fallible and approachable, I decided on the first day of the summer school to do a live experiment and to try to stumble my way to discovering something new, live and in public. A few minutes before the session started, I picked the subject, recursive functions. I began with some examples I knew, then it was time to go exploring. At first, a lot of functions didn't work because they were looking back too far. But then someone piped up, why not just say that f of n is 1 whenever n isn't a positive integer? Good idea, and very easy to try. Soon we had the obvious functions written. So today we probably use total instead of apply plus, but otherwise there's nothing out of date in this piece of Wolfram language code. And in a typical story of Wolfram language helps one think clearly, the obvious function was also very general and allowed a recurrence with any number of terms. So why not just start with one term? And immediately there it was, what we're now calling T311. And then in the same notebook, a plot. And yes, after version 6, one didn't need the show or the trailing semicolon. Of course, as is the nature of computational constructions, this is something timeless that looks the same as it did 21 years ago, well, except now that our plots display with color by default. I thought this was a pretty neat discovery, and I just couldn't believe that years earlier I'd failed to see the obvious generalization of having infinite initial conditions. The next week I did a follow-up session, this time talking about how one would write up a discovery like this. We started off with possible titles, including many audience suggestions, like self-poetic sequences and so on. And yes, the first title listed is exactly the one I've now used in the thing that I just wrote a couple of weeks ago. In the notebook I created back then, there were some first notes, some of which should still be explored, about what could be written. Well, 3 hours later, on the afternoon of July 11th, 2003, there's another notebook with the beginnings of a write-up. By the way, another thing we came up with at the summer school was the non-nestedly recursive function that's given like this, and plotting this. Oh, I don't know why that first line is there. That first line is a copy of the second one. We should just look at the second one. In any case, plotting this gives this result. Bizarrely, reminiscent of McCarthy's 91 function, where n greater than or equal to 396, g of n plus 1 minus g of n is always 97. And g of n equals 386.06 plus 97 times n minus 396. But in any case, a week or so after my write-up session, the summer school was over. In January 2004, I briefly picked up the project again and made some pictures that, yes, show interesting structure that perhaps I should investigate now. In the years that followed, I would occasionally bring nested recursive functions out again, particularly in interacting with high school and other students. And at our summer programs, I suggested projects with them for a number of students. In 2008, they seemed like an obvious, interesting thing to add to our demonstrations project, but mostly they languished until that is my burst to finish this intellectual energy that followed the launch of our physics project in 2020. So here it is, finally, after a journey of some 43 years, I feel like I've been able to do some justice to nestedly recursive functions and provided a bit more illumination to yet another corner of the computational universe. Needless to say, there are many, many additional questions and issues to explore: different primitives, mod, floor, and so on, multiple functions that refer to each other, multi-way cases, functions based on rational numbers, and endless potential approaches to analysis, identifying pockets of regularity and computational reducibility. Well, that's what I wrote. I might just mention, in terms of the history, that many of the people that I mentioned, I personally knew, just a few of them. John Conway, I first met in 1984, Paul Erdos, 1986, Sol Golom in 1981, Ron Graham, 1983, Benoit Mandelbrot, 1986, John McCarthy, 1981, and Neil Sloan, 1983. By the way, in the thing that I wrote, I also included what I think is a pretty complete bibliography of nestedly recursive functions, which lists, I don't know what, some 100 or so different papers that have been written over the years about nestedly recursive functions, though somebody just sent me one more, so it has to be added to the bibliography. But that's what I wrote about nestedly recursive functions. Now, I guess we might have time for a few questions here. Let me see what has come in. Let me see what I can talk to you about. Let's see. Some of these may be in the context of things that I said earlier. D0 says, So you need 3 initial values to kick off the recursion for like P312. Yes, that's correct. Let's see. Ruliad, nice handle, asks what make the functions become 3-dimensional. I think I was showing these plots of graphs that are just showing what function evaluation for f of n depends on what other function evaluation for some f of n minus something. And so that's just showing the graph of dependencies, and one can render those graphs in kind of any form. And I was rendering them in 3 dimensions. The reason that they're cones is that one is kind of these trees are sort of connecting together many things in this sort of in this blue collection, and as it connects all those things together, one's inevitably sort of winding around a cone. Let's see. Dolphin is asking, isn't lambda calculus just generic computation through recursive functions? Well, kind of. As a matter of fact, I'm just about to do an exploration of lambdas. I think it's on Saturday. I was going to do a sort of Ruliological investigation of pure lambdas, the world of pure lambdas. They're also functions that can apply to each other and so on in this recursive way. But the particular form of sort of nested recursion that I'm defining here is a little different than one naturally gets with lambdas. Let's see. Sloth asks, saying it's a layperson question, but it doesn't sound so layperson to me. Is nested recursion treated same manner as non-nested recursion when deriving generating function representations? Do we have non-recursive closed form representations for these functions in general? Absolutely not. It is my strong suspicion that there, in a sense, are no closed forms for most nested recursive functions. The statement there are no closed forms is essentially a statement of computational irreducibility. The only way to know the answer is by explicitly working out the function. There's no way to just have a one and done formula where you feed in an n, and immediately, without going step by step in the recursion, you get out the answer. Generating functions are a powerful technique for ordinary recursive functions. I have no idea what they would look like for nested recursive functions. An interesting question. One could imagine, I didn't try it, it's a thing to try, to write out a formal power series and apply the function. I think it's going to get really weird, because I think that the formal power series in an ordinary recursion, it's sort of local in the formal power series, that the successive terms in your parameter t, or whatever you call it, are that the recursion introduces. It might associate terms of the form t to the n with terms of the form t to the n minus 2 or something like this. But I have a feeling that the composition operation that one does in this nested recursion is going to try and associate the expression, the formal power series for all n with some particular value of n, so that it doesn't have that locality. I think that's my immediate impression of that, but it's an interesting thing to try. Someone should absolutely try it. Let's see, and it looks like that was all people asked about. So I just want to say that this kind of experimental mathematics, Ruliology, it's a lot of fun, and at least for me. And, you know, it's something which, with Wolfram language, it's sort of a very fluent mechanism, very fluent environment for doing these kinds of explorations. And there's just an awful lot to discover. And, you know, I've been doing this kind of thing for 40 years, and I'm just, you know, scratching the tiny part of it, of the surface of what's possible. And I think one of the things that's exciting about Ruliology and experimental mathematics is that if you do it carefully and you do it in a well-organized way, sort of thinking about sort of the minimal cases of things, it's something that's very accessible. It's not like you need to know a whole tower of, you know, a decade of kind of pure mathematical knowledge to make progress. By being organized, thinking clearly, insisting on getting minimal versions of things, you can make progress even without all of that kind of background educational experience. And the more people that get involved in doing this, the better. I think a number of people have been involved in doing this kind of thing since the 1980s. One of the things I hope to do in the not too distant future is to make a better sort of organizational structure. Probably we'll call it the Ruliological Society, for people who are studying Ruliological kinds of things. But for now, we're launching a bunch of these kinds of things at the Wolfram Institute, and that's a place where there's sort of gathering of people interested in these kinds of things. We hope to build it out even further. I just want to say that there's just an awful lot to discover, and it's accessible to an awful lot of people. And really, it's like doing any kind of experimental science. It's a question of doing clean, well-organized experiments that you can explain in a clear way. That's sort of what's involved. And when one does that, it's sort of inevitable, I think. It's at least been my long-term experience that sufficiently clearly done, sufficiently minimal experiments, the results are always ultimately important. And that's a thing that is, so it's kind of a very, I would say, I'm just encouraging people to get involved in this area, because I think it's such a great opportunity for people to do meaningful research that sort of helps build up this tower of knowledge that we can make use of in the future. I think somebody was asking earlier about whether this helps elucidate features of recurrent neural networks, and quite possibly yes. And for me, in thinking about recurrent neural networks, having the intuition that I've got from studying these nestedly recursive functions is something that's just a very useful thing to have when it comes to seeing particular phenomena and realizing, oh, that's what I've seen before in nestedly recursive functions, and so on. All right. Well, thanks very much for joining me, and look forward to chatting with you about quite other things at another time. Bye for now.